Hey BC Cal students, this video is for the ratio test for infinite series. It's my favorite of the series tests because we actually get to do some math. Let's talk about the ratio test. So it's a general purpose test for all kinds of series. Generally, we use it for absolute convergence, which we talked about when we did alternating series. 2 and 3 kind of tie in with each other. For series that rapidly converge, inspecting a couple of terms is really difficult because the numbers get very large, and so it's hard to make sense of them. And 3 is if you have series that contain exponentials or factorials, things like the alternating series test, the geometric series test, or the nth term test don't actually provide any sort of meaningful information when you do them. So the ratio test just works on taking 2 consecutive terms somewhere down the line in the series and checking that ratio. So we're going to know overall a series is decreasing if the next term is less than the current term. So say we take a geometric, we'll use a geometric series to illustrate this principle. So say we had an equals 2 over 5 to the nth power. So we know this series converges because the ratio 2/5 is less than 1. But say we looked at the fourth and let's say the third and fourth term. So that would, if we have n equals 3, then we would have 8 over 125. And then if n equals 4, we're going to have 16 over, so for n equals 4, we get 16 over 625. So what the ratio test does is it takes the rightmost term and divides it by the term right in front of it. So we would have 16 over 625 divided by 8 over 125. And so when we keep change, flip, or however you want to think about it, we get 16 over 625 times 125 over 8. And so we get a 2 here, and this reduces to be 5 because it's 2/5. So we get a ratio that is less than 1. And that's how the ratio test works, is if you take the n plus first term and divide it by the nth term, if that ratio is less than 1, then the series converges. If that ratio is greater than 1, it's going to mean that the n plus first term is greater than the nth term. So ultimately, that series is going to converge because you keep adding larger values to the series. And the series is going to be, the ratio test is going to be insufficient if we end up with a case where n equals 1. So a lot of this just uses a lot of algebra. So when we're doing example 1, we're determining if the series 3 to the n plus 1 over n times 4 to the n converges. Now again, we're just basing this on the limit. We're looking at the limit in absolute value of a to the n plus 1 over an. So an plus 1 over an. If we have negatives, the absolute value means that you can just disregard the -1 to whatever power. We'll see that, I think, in example 3. So for example 1, again, we have the series from n equals 1 to infinity of 3 to the n plus 1 over n times 4 to the n. So what we need to do, and we want to keep good notation for this, we're going to have the limit when n approaches infinity, and in absolute value, we're going to have, so we need the n plus first term is going to be 3 to the n plus 1 over n plus 1 times 4 to the n plus 1. And so then, so this is our an plus 1 term. And so we're going to divide that by the nth term, which is always going to be the series that you start with. So we're dividing by 3 to the n plus 1 over n times 4 to the n power. So most of the time you can kind of skip this step. So again, we have the n plus first term, and in the denominator we have the an term. So if we keep going, keep your limit. We have the limit when n tends to infinity. That would give us 3 to the n plus 2 over n plus 1 times 4 to the n plus 1. And so when we're dividing by 3 to the n plus 1 divided by n to the n times 4 to the n, you multiply by the reciprocal. So we're going to have times 4 to the n times n over 3 to the n plus 1 power. Now, because none of our terms are actually negative, we don't really need the absolute value. And at some point, in my opinion, I would just drop it, but I will keep going. So we're still taking a limit. So we have our limit as n goes to infinity. And from here, you should group your terms. Like some of you can just can't look at this right now and see what you can cancel. But for those of you who cannot, group all your things that look alike. So that means that we need to have the 3 to the n plus 2, that's over 3 to the n plus 1. We're going to group the 4 to the n's. So now we have 4 to the n. We're going to extend our fraction. 4 to the n plus 1. And then we have n over n plus 1, and we'll put that in parentheses. So we can look at this at, I'm sorry, this is out of frame, excuse me. So we have 3 to the n plus 2 times 4 to the n times n over 3 to the n plus 1 times 4 to the n plus 1 times n plus 1. And again, you want to just group all of the things that look alike, and then from there, you can cancel as necessary. So what happens is 3 to the n plus 2 over 3 to the n plus 1, we subtract the exponents, we end up with a 3 to the first power in the numerator, and then 4 to the n over 4 to the n plus 1, we end up with the 4 to the first in the denominator, and then we have n times 4 times n plus over n plus 1. So all of this reduces to be just the limit as n goes to infinity of 3n over 4 times n plus 1. So the neat thing about the ratio test is that the limit is written for n. So the 3/4 does not matter. So you can put the 3/4 in the front and then just calculate the limit for n going to infinity of n over n plus 1. And so we know that this limit is 1 because, again, when the degree of the numerator equals the degree of the denominator, the limit is the ratio of the leading coefficients. So this is equal to 3/4 times 1, which equals 3/4. Now, again, according to the ratio test, if the limit that we get is less than 1, then this series ultimately converges. So down here we'd write, we're just going to call this an, so we don't have to write the entire thing. We would say the series from n equals 1 to infinity of an converges by the ratio test. And this is all of the work to verify the ratio test. So again, we take the n plus first term, divide by the nth term, simplify this, simplify some more, cancel, pull out anything that's not written in terms of n, and then calculate that limit. For example 2, we have pi to the n over n factorial. So we're going to take the limit as n tends to infinity of pi to the n plus 1 over n plus 1 factorial. Now, instead of dividing by pi to the n over n factorial, we're just going to immediately multiply by n factorial over pi to the n power. And again, we don't really need the absolute value because neither pi nor n is ever going to be a negative number. So up here, remember the n factorial is equal to 1 times 2 times 3 times blah, 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 all the way out to n. You just take all of the numbers, all of the integers from 1 to n and multiply them. And so then n plus 1 factorial is equal to 1 times 2 times 3 times blah, blah, times n plus 1. Now, another way to write this is n plus 1 factorial is really n factorial times n plus 1, because n plus 1 factorial has to contain n all the way down to 1. So that's useful because when we simplify this, we get the limit when n tends to infinity. So pi to the n plus 1 over pi to the n is going to give us a pi in the numerator, but then n factorial over n plus 1 factorial, it will write it so you can see. So n factorial is going to remain, but in the denominator, n plus 1 factorial is n factorial times n plus 1. And so what happens is the n factorials can cancel or they divide to equal 1. And so what we're left with is pi times the limit when n tends to infinity of 1 over n plus 1. And in this case, because there is no n in the numerator, we know that this is going to converge to 0. So this limit is equal to pi times 0, which equals 0, which is less than 1. So we would again say that this series converges. You know what? Let's write a complete sentence. So we're going to say the series from n equals 1 to infinity of pi to the n over n factorial, not equals, but converges by the ratio test again. And you can use the ratio test to prove all kinds of convergences. You can use it for the geometric series. You can use it for the P series. It works out for all of those things, but generally those other tests have more specific criteria which make them shorter to do. But generally speaking, the ratio test is good for a lot of convergence tests. So for example 3, we have negative 1 to the n times the square root of n plus 1 over n plus 1. You know what? That actually could, you know what? Let's make this an n plus 2, because then if this was n plus 1, you could just say that's negative 1 to the n over the square root of n plus 1 in the denominator. So we're going to move this up. Our limit is going to be the limit as n goes to infinity of, now, if we're doing this in absolute value, the negative 1 to the n goes away. So effectively for the ratio test, you can just ignore the negative 1 and then do the limit of everything else that would remain. So we're going to have the square root of n plus 1 plus 1. So n plus 1 plus 1 over n plus 1 plus 2. And so remember, we'd immediately divide by this, which is the same as multiplying by the reciprocal. So we're going to have times n plus 2 over the square root of n plus 1. And again, you should group the things that look alike. So we're going to have the limit when n goes to infinity of the square root of n plus 2 over the square root of n plus 1, and then multiplied by n plus 2 over n plus 3. Now, a property of square roots is, I'll show you up here, the square root of a divided by the square root of b is equal to the square root of a over b. You can divide the two things first and then take the square root. So what we get is the limit as n goes to infinity of the square root of n plus 2 over n plus 1 times n plus 2 over n plus 3. Now, again, we're taking the limit of this thing. So the limit is distributable over a product, meaning that we could make this the limit as n goes to infinity of the square root of n plus 2 over n plus 1 times the limit as n goes to infinity of n plus 2 over n plus 3. But that's just unnecessary. What actually happens is when n goes to infinity, you can ignore the square root. Really, you have the degree of the numerator equals the degree of the denominator. So the limit is the ratio of the leading coefficients. So this limit is 1 and this limit is 1. So we end up with 1 times 1, which equals 1. So remember we said that the ratio test is insufficient if the limit equals 1. Because then what that means is that you're basically adding 1, as far as you know, you're adding 1 over and over again to the sequence. So seemingly, if you could reach a conclusion from this, it would be that the series has to be divergent, but there's special cases for which that's not true. And so in a later video, we'll talk about how you can test the convergence or divergence of a series like this. It's called the limit comparison test or direct comparison, and we'll talk about it in another video. But in this case, we get 1, so we would just say ratio test is inconclusive. And so for the last example, we have 2 to the n plus 1 factorial divided by 12 to the n. So again, this is one of these cases where inspection is really difficult because using, like even if we start out with n equals 1, we're going to have 3 factorial, which is going to be 3 times 2 times 1, which so 6 over 12. But then when n is 2, we're going to have 5 factorial over 144. It's hard to know what happens when n is small. This series converges very quickly. So instead of using a handful of numbers to see a pattern, what we're just going to do is directly apply the ratio test again. And so it's the same process where we have the limit when n goes to infinity. And this time we're going to have 2 times n plus 1 factorial over 12 to the n plus 1. And so then again, like the first thing we would do, the next thing we would do after this is immediately divide by 2 to the n plus 1 factorial over 12 to the n. But that is going to be the same as multiplying by the reciprocal, which would be 12 to the n over 2n plus 1 factorial. So if we do some simplifying over here, we can just use the rest of this space to finish the problem. It won't take much. So when we distribute, we get 2n plus 2 plus 1 factorial. So that's really 2n plus 3 factorial, which is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So this factorial, so 2n plus 3 factorial is 2n plus 3, go down 1, 2n plus 2, go down 1 again. You end up with 2n plus 1 all the way down to 1. And so what happens here is in the numerator, these two things would remain, in the 2n plus 1 factorial over this turns into a 1. So what we're going to do is rewrite this as the limit when n goes to infinity of 2n plus 3 times 2n plus 2 times 12 to the n over 12 to the, well, actually, we don't need to write the 12 to the n plus 1, 12 to the n. This one just goes away completely, and we're just left with 12 to the first power. And so we have 12 times, I forgot the 2n plus 1 factorial up here. So you know what, just start it over. So over here, we're going to have the limit when n goes to infinity of 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And again, the 12 to the n, 12 to n plus 1, they cancel so that you're just left with a single 12 in the denominator. So we have 12 times 2n plus 1 factorial. And what happens is the 2n plus 1 factorials, they cancel. So what we're left with is the 1/12 can go on the outside. So we have 1/12, the limit as n goes to infinity of 2n plus 3 times 2n plus 2. So if you wanted to, you could rewrite this as 4n squared plus 6n plus 4n, so plus 10n plus 6. And what happens is if n goes to infinity, this is going to converge to infinity as well. So what we're going to end up with is something that's divergent. So over here, again, if we call this an, we could say the series from n equals 1 to infinity of an is divergent by the ratio test. All right, so a quick review of the ratio test. We use it when we see series that generally contain exponentials or factorials. And it's also used for absolute convergence. And so the three criteria are the series converge. Well, the three conditions are the series converges absolutely if the limit is less than 1, diverges if the limit is greater than 1, and the ratio test is insufficient if the limit equals 1. So again, the way you would end up at 3 is that you probably just try to do the ratio test initially, which is always a good thing to do if it seems like you can't figure out any other test to use. I would always start with the ratio test, but some things are apparent like the geometric series or alternating series. But even when you do the alternating series, you end up with having to test absolute convergence anyway. So the ratio test is always a good place to start if you're looking for a test for convergence. In the next couple of videos, we're going to cover the nth term test for divergence, the limit comparison test, and direct comparison. And after that, we're just going to jumble together a bunch of series and see if we can determine which test is most appropriate to determine convergence, because that's how you'll be tested upon that. You won't see questions that are isolated for like geometric series or alternating series. Some of them are, but a lot of them require that you know, like you can recognize each one of the tests for multiple options. So I'll see you guys in the next video. Stay safe, stay healthy, and be well.